Okay, hello everyone. This is the additional video for basic math class. So we are going to discuss about the exponential function, but before I am going through all the details, we can start the exponential by taking the exponent. For example, if I take 2 with power of x, okay, let's say this is our f of x. We can start by taking, let's say we start from 1, okay. We take 2, it means that, okay, if you want to make that, okay, and this is 2. And then if we increase more, for example, if we increase 4, 16, and then if we increase, let's say 8, okay, so it will be 256, right? If I take 10, it will be okay. So the point is, what I'm going to tell you is from the start until this one, from x equal 1 to x equal 10, we see that the magnitude is going to be triple digit, right? It's going to be triple digit. From 1 digit it become 1,000. So which means that exponential is, if we are illustrate with how fast it is really fast, right? So it's really the function increase significantly. Okay, so we start to define the exponential functions as with this a symbol. A is the base. Okay, so let me write here the base. So a need to be positive number, and it should not be equal to 1. Okay, should not be equal to 1, because if we take 1, then it is meaningless, right? It's supposed to be just it's supposed to be at least 2, okay, at least 2, or maybe more than 1. Okay. Okay, so if x, for example, if we have this, and if x is irrational, then we approximate x by rational numbers, which means that if we take, let's say, square root of 3, this could be done by some approximation, because we are going to see, we are not going to see the full answers, the complete numbers, but it will be like the long decimals, right? So since this is irrational, then if we take a and then with power of square root of 3, then we could see approximation okay. So if we see, when we move this from the left to the right, it will be getting closer to our goal, which is a with power of square root of 3. Okay. You can try this in your calculator if you would like, but I think that would be just that. I think we can move on to wait, where is, oh, sorry. We could move on to the graph of the exponential functions. Let me write here. Okay. So graph, we can start from here. We have the blue and the red. So we can start from the red first. So the red one is this base. So base is 3 with power of x. So we say it's positive. Okay, it's a positive. A is positive. But on the left side, on the blue one, we can see that this 1/3 is 3 minus 1, right? So this is actually 3 minus x. So you could see that we can sense that these two graphs are reflecting each other on y-axis, right? And you could see that this could be the reason, right? So when we change the x with the negative counterpart, with its negative counterpart, this is actually, so if this is f of x, okay, if f of x is 3 with power of x, then the f negative x will be this, okay? And this could be like intuitively we have known before, right? Okay. So yeah, so you could and this approach could be helpful when you are dealing with a any functions that's related with the exponential, like especially the natural exponent. Okay, if you are going to see how the function getting close to the x-axis or getting infinitely large when we are increasing the x, okay, and in opposite, we can also see the same behavior on the counterpart, which is the f in negative x, okay? And we see on the whole possible functions for exponent. For example, if we increase, let's say we are starting from the right side here. So we see that we have 2 with power of x, and then we have 3. Okay, so let's compare this 2 and 3, the base 2 and the base 3. The base 2 is over here, right? So what should we taken care of are, when you are increasing the base, actually your functions is getting faster, okay? Which means that on the same x, for example, let's say the x is around here. Maybe this is half, okay? So if I take this, then the one that is going to reach the highest point is 10 with power of x, right? Okay. So this purple one, of course, the curve is it's not finished yet. So you could see that it's actually getting larger, like that, right? And then we can see that the 5 power of x is below, and then 3 power of x, and then 2 with power of x, okay? And the same thing when we are looking at its negative counterpart, or the rational with power of x, you could see that the 1/2 it's going to be on the left side, and 1/10 on the right side of the whole rational with power of x, right? So you can see that it's kind of reflecting each other, okay? But my suggestion is, if you are going to like make sense of all of these things, you could start from this one first, okay? So the right one, the right one first, and then after that you can reflect that, and make it on to the left. Okay. 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 I think we can move on. The next part is the transformation, as also we've done with the previous polynomial and rational functions. So in the exponent, what we are dealing with is we are going to see that since it is the scale will be changed according to the power, so it is best for us to know what will be the assumption. Okay, so we start with this base of 2 with power of x, and then we are going to shift upwards a 1 unit. Okay, so it's not the same as we move the base. Okay, let's say we move the base, just translation. For example, if I take this, let me make this a little bit so that you can see what I do mean. Now suppose that this is our curve. So if I move this 1 unit upside, it's not really fit, right? So what is happening here is actually we need to set some rules. Okay, we need to set some rules, which is that the 2 power of x, when x is 0, y is 1. Okay, so which means here. Okay, and when this function, the 1 plus 2 power of x, when x is 0, then y is 2. So that is going to be the first indications. Okay, so we need to cross exactly at the y equal 2. So this will be the let me just erase for a while. So this will be the point that the curve need to cross. Okay, and then what else that we are going to consider is the y equals 0. So at y equals 0, so if y is 0, it's impossible, right? It's impossible. Well, if you learn calculus, you know that we can get close to, right? But since this is the pre-calculus, so we are not yet using the limit. So you could use some logic that if y is 0, then it is impossible for x, okay, to be like to solve for x, right? Okay. So the best way is for this setup are if we, so as, let me write here, as x is getting larger to the left or negatively large, okay, then y is getting closer to 0. Okay, so I didn't write limit, right? So I can write like this. Now the same thing for this red curve, since this 2 power of x is getting close to 0, then the let's say we say the asymptote is move away from y equals 0 to y equal 1. So this is the or maybe right with the yellow. Okay, and this will be the asymptote for the blue one. Okay, so I hope you get the idea. So this is the setup that need to be done, and then afterwards you can draw a typical exponent. So you need to at certain level. So I think you could see that at the very early part here, it seems like similar, but afterwards it's getting a little bit different. So the for somehow we are going to see that this curve will cross at some point. Okay, because do you know why? Because if we think clearly, that if we take this and compare with this, when x is larger, so as x is larger, the 1 is become more and more meaningless. So somehow we could see that these two curves are getting close to each other, because this one is not really that meaningful, right? Compare with this 2 power of x. Okay, I hope you get the idea. Okay, I hope you get the idea on how to transform. Okay, the rest is the same as usual. Okay, the rest is the same as usual. Okay, now the same thing here. If we reflect with x-axis, on x-axis, we basically minus the function. So this, let's say this is the f of x, and this will be the negative f of x. Okay, a little bit different from the previous one, which we have here. Here, this is reflecting to y-axis. The x inside the f, that is going to be changed, right? Okay, so back here. Okay, so we can reflect that, and then the same thing with the shifted through the horizontal shift. Now this is we need to take care of this with some correct thinking. Okay, so start with the function. So this is the function. Okay, and we would like to take the function. We would like to take the functions and shift it. So this means shift to the right. One unit, right? Okay. And then we could see that the y equals 0 is the interval. So y equals 0 is the asymptote, sorry. So this will be the asymptote. This y equals 0. So what's the difference here? The difference is this part. Okay. So we would like to have, so when x is 0, y is half. Okay, so we get the intercept for in y-axis, which is y equal half, or we say the intercept will be 0 half. Okay, so for sure the graph should cross that point, and then the rest will be following the same behavior as the original graph. Okay. And similarly, when we take to the left, okay, which means that when x is getting close to so when x is getting close to negatively large, or when x is going to the left, then we see that the f of x is getting closer to 0, which means that this -1 also not much affected, okay, because we only see that the affected one is only on this part here, okay, which take two different curve on here. But when we see on the left, it's going to converge into one value. It seems we see that. Okay. Now another thing, aside from transformation, in the exponent are the natural exponent function. But perhaps if you have time, if you want, maybe I will attach another video that explain about compound and interest. Okay, that's usually we are getting when we are put money into the bank. Okay. So let me write here compound interest. But I would just like to share the conclusion from this compound interest. Maybe I will attach another video later on. Okay. So this compound interest is basically, we could rewrite, and then we can find this expression. Okay. So we have this formula 1 + 1 over n, and then the whole thing we are going to power with n. Okay. And based on the number n, we could see that from n = 1, 5, 10, we see that the numbers is getting change also. But from 100, 1000, 10,000, the change is not really that significant. It seems that we can see that it's a little bit negligible. So when we are having 1 million, we are see this number. And long story short, we can write that a special number we call the Euler number, or E, is and we are not sure how many decimals it will lead to. Okay, how many? Okay, but we know that this number will show up on some natural phenomenon or statistics. Okay, and this number will be the base for natural exponent. Okay, so maybe it is interesting. Okay, the question will be perhaps why using E, for what and why, right? So based on the explanations, okay, let me write here. Okay, the natural exponent function we can write as e with power of x. So the base is, we are getting e. So again, here I would like to emphasize that e is a number or constant. So it's not a variable. Okay, it's not variable. Okay. Okay. Now, if we are trying to make our so that we can understand why we are using e, maybe from the visuals we can see we can set up the base 2 and the base 3, and then if we are going to set up e, it is going to be in between 2 and 3, or we could say it is getting it is closer to 3 to the power of x, since e is start from 2.78 something something, right? Okay, so this is y e to the power of x. Okay, so this is, we could write, since 2 e and 3 and then the graph is in between okay. And then we could also take this approach as well, which we get e with power of x, and then we get e with power of negative x, which is a reflection on y-axis, right? Okay, the same thing. Okay. Okay, now let's continue to the logarithmic function, which is the counterpart of the exponential. Okay, so recall that in the previous section about the inverse, we know that if we write the f inverse of x equal y, then we can say that f of y is equal to x. Now the same thing that we know that the exponent is actually the inverse of the logarithmic function. So if we set the definitions based on, let's say we have a base a, okay, and we denote the logarithmic function with that base is equal to log with subscript a. This means that we have a log with a base number of a, and we are going to define this as let's say we have y equal to log base a of x. Then this is actually the base a with power of y is equal to x. So in logarithmic, we are going to find how many powers should we take to take the base of that number to make out the x. Okay, so we are raising this y to make x. Okay, or we could write a with power of y equal x. Okay? Or we could write in the terms of log with this. This is actually the inverse. Okay, so this is actually inverse of each other. So exponent and the log, they are both inverses each other. Okay, so this is how we could break down the log and exponent. Okay, so the base is a and the exponent is y, and x is the number that we are going to get in after take the power, after taking the power. Okay, so for example, if I have 2 with power of 3 is equal 8, we can write this as log 2 and then 8 equal 3. Okay, or we have maybe just like a and then equal b. This means that this is log 5 b equal a. Okay, I think you get used to this log, right? And then we have the inverse property. Oh, I think we should write here. Let me write. Make it a little bit smaller for a while. Okay. So based on here, okay, this is actually by the definition of the inverse, this is y equal x. So if we reflect the exponent to this line, y equal x, we get the symmetrical based on that line, and then we get the logarithmic functions graph. Okay, this is by inverse property. Okay, and then let me put the picture. Okay, I think we can just skip this first. Okay, and then let me put here down here a little bit bigger. And some of the interesting property on this log, if you see, so this is log with different bases, okay, from base of 2, 3, 5, 10. And when you see in the brief, you will see that the base 2, it has more, it's getting on the top, right? It's getting on the top. And yeah, for example, if we take some, maybe x equal 3, 4, 5, maybe this is 2, 3, 4. So when x equal 2, for example, you'll see that this is actually asking, for example, if x equal 2, like for example like this, it means that we are wrong. So we are going to take a 10 with power of something equal to 2. Let's say this is y, right? This is y. Or if we take 5, the base 5, let's say equal to x equal 2, this is y. So this will be 2 or 5 with power of y equal 2. Now imagine what kind of y would be. So for 10 to make it into 2 should be really, really small for y. So that's why the purple color is the lowest, and then blue, and then black, and then red. Because when it's going up, it means that we are getting to, for example, when x equal 2 for this one, so log 2 equal y. So y is equal 1, right? So y equal 1. So it's perfectly here. Okay. So I hope you get the idea. That's because of the base. Okay. And now the interesting part is also all the log functions, they are getting the same property, which is they are always get cross this x equal 1, because when x equal 1, it should be 0, right? So for example, log 3 1, of course this should be 0, so because 3 to the power of 0 is 1, and then log 5 1, this is also 1. Okay, so all the functions, log functions, they should crossing this x equal 1. Okay, all right, I think that is okay. I think we can move to the transformation. So the transformation, similar to what we have in the exponent, we could start to see the reflections. So looking at this g of x and f of x. So looking at the g of x, this is actually so g of x is negative f of x. So we reflect with respect to the x-axis. I think it's the easy to understand for this one. This is also similar, but since we are symmetrical on y-axis and nothing wrong with this, so this is basically, we say that the h of x is of h minus x. So we reflect with respect to the y-axis. And then we have the shifting. So this shifting, for shifting vertically, I think not a problem, because you basically plus the number or reduce the number, so you can go up or go down. So basically it depends on how much you add, how much constant you add to the function. So you will see that it will move 2 units upwards or downwards. We have the vertical shift. Okay. Now the interesting part is on the horizontal shift, which we need to take care of the asymptote. Okay. So remember that the original functions for the log, it's always having the, so we have asymptote here, which is x equals 0, which means that the log, so let me give you the idea. So when the log is with any base 1, this should be 0. But if I take log with any base 0, this could not be defined. This could not be defined because anything with powering with any numbers, it couldn't have any 0 as a result. So this couldn't be defined. So that's why it's never crossing the asymptote. Okay, so we have the asymptote. That's need to be understood. Okay, and then when we shift the horizontally, for example, here we shift to the right, 3 units, which means that if the original one is getting cross at 1, so we are going to getting cross at 4, and we could check. Okay, we could check how it feels and every time you are moving your function or transforming your function, you could always check. You could always check your x, just putting back the x on here, and you'll see that it's equal 1, which means it's 0. So it's true that it is going to cross the x-axis, right? Okay, so shift it to the right 3 units, and then the rest is basically tracing all the original functions. For example, you have the asymptote x equals 0, and then because of the shifted, you have the asymptote on x equals 3. Okay, and then the rest you can just trace out all the same with the original functions. Okay, so that's the transformation. Okay, and then another I think property that should be familiar with is the first, we now have the common logarithm. So if we are just telling you the log without any base, it's indicating that it's actually the base 10. So base 10 is, we call the common logarithm. Okay, and with the same with a similar approach, then if we have a base e, as we did in the exponent, we have the base e, we call that as a natural logarithm. So we could write the natural logarithm as ln. Okay, and that means it's a log with base e. Okay, so we can write ln x as a log with base e of x. Okay, or we could just simply write ln. Okay, and it's from natural, so it's like logarithmic of natural. Okay, or natural logarithm. Okay, and of course, same thing what we have in the inverse property. We could also, looking at the ln x and e to the x, they are inverses each other. Okay, and this is property of logarithm. I think this is, and similarly we have property for the natural logarithms. Okay, so this is what we have before. So I think this both property, they are the same thing. The difference is the natural logarithm has a base of e. Okay, so basically this is from the inverse property, and then the exponent property. Okay. So yeah, I think you will get more familiar with this when we learn on the law of the logarithm. Okay. Now, okay, I will maybe elaborate later on. Okay. Now, if you discuss the logarithm, I think it's best to know some of the laws that is pretty useful and helpful in terms of solving some algebra equations. So if you see this law, it basically has at least three. Okay, so we say that we are having the combinations, and then by multiplication, and then division, and then the last one is if we have a power c, and then we could basically getting the c down and getting it in the front. Okay, so let's start with the first one. Is we can combine this all together. So let's prove this a little bit. Okay, so let log base a of the capital A equal u, okay, and then log with base b, or this is a, sorry, the same base, and b, this will be maybe v. Okay, so this will be a with power of u equal a, right? And then this a with power of v equal to b, okay, in the exponent form. Then if we multiply this a with b, which means we are multiplying the a with power of u and a with power of v. Okay, or we could write a and then a, this will be u plus v. Okay, now remember that we have a property on the previous sections, which we'd say that if we have log a with power of x, this is simply just x. Okay, so this means that this will equal to u plus v, or log a of a and then log a of b. So this is now have been proven that this is true. Okay, so this is for the proof. Okay, proof for the first one. And the same thing with the second one, with the same symbolization. We can write log we could write this as, so to get a, or maybe let me write here, to get a, we are going to have a, and I will divide b and then multiply again with b. Same, right? Okay, I can write like this. So, and then we can write log a, this is a over b, and with the first proof, with the first law, we can write the combination of this, right? Okay, so log, we move this to the left side, equal log minus log a b. So now proven. So we are using the combination law and then proving the division law. Okay, now the third one. So let me write again. So let log a, so a u is capital A, so log a, and we have a and then with power of c. This is actually, we can write a with power of u and then power of c. and then we can write this and combine u and c, and this is actually just u c, okay? Or this is c multiplied with log base of a. So that's why if we look at this, it's simply just saying that this c can be turned down at that, okay? So that's all the three, I think, important laws for logarithm. And let me show you how to express and how to use in a simple way. So if we want to evaluate like this log, like this one, so we want to combine. Okay, so for the first one, since it's the same base, it's already in the same base, then you need to check first whether it's the same base or not. So we are having the same base 4. That means that we are going to multiply this 2 and 32. So this will be log 4 64, or this means that how many powers should we take on 4 to get 64? It's 3, right? So because 4 power of 3 is 64, so this will be equal to 3. Okay, because 4 power of 3 is 64. Okay, now number B, we have subtractions, and again it's the same number of base, it's base of 2, so we are going to have 80 divided by 5, which means it's going to be 16. So how many power should 2 taken over so that it's going to result 16? It's 4, right? It's 4 because 2 with power 4 is 16. Okay, now the third one, this is basically, let me write. So this is basically log 8 with power of -1/3, or this is basically just taking cube like that, or perhaps we could see that this is 2 3 and then multiply that, and then we can also write this as log half, and you can use calculator to get the approximation number. So this will be 0.3001. Okay, and then this is we evaluate it. Sometimes we don't need really to evaluate, we just combine the expressions as we are see and observe on the algebra, like this one. Okay, so if we want to combine into a single logarithm, we need to make sure first the base need to be the same. Okay, if they are not telling you the base, it means that this is the base 10. Okay, as I mentioned before, it's common logarithm. So for number A, we could write that this 3 on the front, we could move it and make it into cube power like that, and the same thing with this one, we can make this with power of half. So then we can combine all together and make a big chunk of a single log like this, and then that's it. Okay, because we are nothing else, like what we like, we don't really need to do anything, right? So we just combine them all together. Same thing with the number B, it's going to be s cubed plus ln t half minus ln t squared plus 1 with power 4. So we could combine first ln, and then this will be s cubed t 1/2, and then minus. But since it's minus, then we are going to see this is going to be divide by, okay, and then that's it. If you want to write in the square root, that's okay. Same thing. Okay, easy, right? And warning. Okay, let me write, because I see also in your calculus you sometimes forgetting this law. So let me write, this is sometimes you write and express this x plus y and then taking it into these two separate equations, and this is wrong. Okay, this is wrong. You should have multiplication. So this is true. For this one is true. But for the first one, that's wrong. Okay, that's wrong. So don't forget about the basis on the rules. Okay. Another important rules or law that is applied in the logarithm is the change of base. Okay, change of base. So let me write first what is change of base. So suppose we have y log with base b of x. Okay. So we can write b with power of y is equal to x. Okay. Now this is interesting. So let me write again with some distance, and then we take log. Let's say with base of a. When we're doing this, we can input log with any base of 10, 9, 8, any base. Okay, and then we try to solve this, and we have y log of a of b, and this is equal to log a x. We can write y in terms of log a x divide log a b. So we could write here the change of base. I think I have somewhere here. Okay, so this will be the change of base formula. And a it can be any number. Okay, it can be any number. And if we put x equal 1, if x, or not equal 1, x equal a, sorry. If x equal a, then log b of a is 1, because log a of a is 1, right? So this will be, so actually you change and you get the new law formula. Okay, so you're basically changing b in a, and then you write 1 over log a b. Okay, see the difference. Okay, so this is from the change of base. So this is really useful formula. You can use it for manipulating your structure, your algebra, and helping you to solve any equations related to log, especially. Okay, so yeah, that's the basis idea for some law and logarithm. The next part will be some equation that might have and how to solve that equations. Okay, in terms of exponent and log. Okay, so let's start to look at some equation that we need to solve. Okay, or maybe later you will see also when you're solving some algebra that has exponent or log, how to solve them. So first, if we have this exponential equation, we have two questions here. 5 to the power of x equal 125. I think it's very simple. Basically, we need to make sure that the left part and the right side, if we can make some exponential forms, then write it. So 125 is 5 to the power of 3, right? And when this happens, it means that this has the same base. So that's the key. We need to make sure that this base is the same, and we can equal them together. So x is equal to 3. Okay. The same thing with here, it's already in base 5, which means that this is 2x equal x plus 1. So x equal 1. So I think it's very simple. Okay. Now if we look on this and how to solve this, we can first isolate and take log. I think that will be very reasonable. So for example, if we write 3x2 equals 7, okay, let me maybe write with some distance and take log both sides. Maybe just make it base 10 to make it easy to calculate. So x plus 2 become here. This is log 3 and this is log 7, or x plus 2 is log 7 log 3. So x is log 7 log 3 minus 2. Okay, so basically you can you could calculate this through calculator. So we can find the approximation for x is maybe around negative, because it's minus 2, so it should be negative. Okay, that's the some simple example for exponential that we might have in our maybe more in the future works. Okay, another thing, still in the exponential, if we have e like this, what should we do first? First we simplify it. Okay, we simplify it like that. Okay, and then the next thing is, or maybe let me write first, this is 2.5, right? 2.5. And next thing is we can take the ln. This can be 2x, and this will be ln 2.5, or x is ln 2.5 divided by 2, or if you want to use calculator, we could get 0.458. Okay, now it's getting more interesting here. So we have something like this. So we have e with power of 2x, and then minus e to the x and minus 6 equal to 0. So how to get into this? So letting the e become any other variable maybe sometimes is helpful. For example, we see that this is e with 2x, this is e with x. Okay, so if we say that we are going to make e to the x as, for example, a, so we can rewrite the equations become a squared minus a minus 6. And simply this is just a normal quadratic equation that you can solve easily. So we can say that a, and this is just negative 3 plus 2, right? Yeah. So a is 3 and a is negative 2. But it's not over yet, because we are going to turn back a into e to the x. So e to the x is 3. E to the x is negative 2. And this one, no solution, right? Because e to the x is basically a positive functions, right? It cannot be negative, right? You can think with random x, they are impossible to be negative. Okay, so this will be no solution. So the only solution is for the left one. So the x is basically ln 3. Okay. So every time you get the answer or the solutions for these supposed to be like a quadratic, you need to check each one of them, because sometimes there will be, maybe some of them are not solutions. Okay, so you need to check. Okay, like this one is no solutions, right? Okay. Now the other one, we have this. So basically, so aside from we can use other variable to help, or we could just simply factor the common factors in the equations. For example, here we have x and e to the x that we can factorize. So let's factorize that. So we can factorize x and e to the x. Or maybe let me write, maybe to make it more clear, let me write 3 and then plus x and then e to the x here, okay? And this equals 0. So the one that can make these equations equal to 0 is this, okay? Because the e will be a positive function, right? So it doesn't really have a meaning in here to make it 0, right? So the only way that we can solve this is x equals 0 or 3 plus x equals 0 or x equals -3. But is it true? Then we need to check. Okay, so check back the x equals 0 back to the equation. So 3, 0. So this will be 0, 0, and this 0 is true. Okay, so it's correct. Okay, and then the x equals -3, we can check 3, -3, e, -3, plus this will be -3 squared, and then e, -3. So we have -9 plus 9. So this will be 9e negative plus, or this is negative, this is plus e, and this will be equal 0. So it's also true. So both are our solutions. Okay. So x equals 0 and x equals -3 are solution. Okay, so don't forget to check every time we have finished the or solved the, seems to be finished, but it's actually not yet complete if you are not checking the solutions. Okay, so always check the solution at the end. Okay, let's continue for the other question. Now if we are focused on the logarithmic equations, so we have some problem here. Solve the equation. So how to solve this? So basically we are going to stick with this property. If we have this, then x is equal y. So we are going to see the left side of the equation and the right side of the equation, and then how does it looks like, how it's the base, whether it's the same or not, and we are going to make it equal. Okay, try to make it equal, and then we are going to have the solution based on that equation. Okay, so here first thing is the right side of the equation, it has plus, so log something something plus something something. So we can combine this, right? We can combine it, and all the log is on the base 10. It's not having any number there, so we can assume that it's a base 10. So we can just multiply the inside equation like that. So basically this is a log, and this will be x squared plus x plus -6, right? And this will be log the same. So since this is the same log, the same base, so we could write x squared plus 1 equal x squared plus x minus 6. Or if we solve this, so x equal 7. Okay, and you can also check this x equals 7 is satisfy the original equation, because we can substitute 7 here, 7 here. It will be satisfied. So this will be 49 plus 1 is 50, log 50, and this will be 5, and then this will be 10. So multiply, it's also 50. So it's the same. So it's satisfied. Okay, so x equals 7. That's our solution for this one. Okay, next, if we have this, we have ln x equal 8. So remember that ln x, we can just use the definition of the ln itself, which is e or we can write ln is log base e of x. So x is e with power of 8. But you can also see from this perspective also. So we can add, or we can powering e with those numbers and ln x, so n and e with power of 8, and this will be x. If you are getting used to the right one, I believe it is really helpful. This property is really helpful. Okay, but if you are not really familiar with this one, you can start from this. Again, this is easier to understand because we are discussing this previously, right? If you are familiar with this, this will be the green one here. It will be really helpful. Okay. And now for b, we have log with base 2. Okay. So this simply 25 minus x is equal base of 2 with power of 3. So this is just that. So x is 17. And we can also check 17 here. So 17 will be 8, which means it satisfies the equations, right? Because 2 with power of 3 is equal to 8. I think very simple. Now the next part, solve this equation here. So 4 plus 3 log 2x equal 16. So first we simplify the equation. Is equal 12. And then we divide by 3, go 4. Okay, and then 2x, because it's base of 10, we can just write 10 with power 4. So x is, this is 10,000 divided by 2, it's 5,000. I think very clear and simple. We can also check if this is 5,000 here. We have log of 10,000, which is 4. So 4 multiplied by 3, 12 plus 4 is 16. So it's also satisfied. Okay. And now the other one is this one. Okay. So similarly, you see the log, the same base, we can combine. Okay. And this will be 1. Okay. Or 1 is actually log of 10, right? So basically, you can write this equal to 10, and we solve this this quadratic equation, finding the roots. So x is plus 4, x minus 3. So we have x equal negative 4 and x equal 3. And again, we are going to check all these terms inside the original equation. So original equation has log. We check. Let me write first this. So let's check now with negative 4. So negative 4, checking here, it's now getting undefined because log negative 2 is undefined. So this is our not solution. No solution. Not a solution. If we check x equal 3, let me use different color. So 3 is log 5 plus log 2. I think this is correct, right? This is log 10, and it's true that this is the solution. So only solution are x equal 3. Okay. Okay, I think that will be some just a small example. I think later on, if we have time, then perhaps we could have more exercise. Okay. So yeah, I think that's it for this additional video, and this will be the chapter 4, right? Chapter 4. So after polynomial, we and rational function, we are having the exponent and log, and we are going to have more exercise later on. Okay.